Hello everyone. Sharif, Sasha, with my colleague Samuel Joga. We shall be taking you through introduction to machine learning. First, we do start off with a brief definition of what machine learning is, which is a field of study that gives computers the ability to learn without being explicitly programmed. And this means that the computers are able to train on the data which they are using without having specific rules that they are following. And for machine learning, the most I think that is being utilized is data to solve a problem. And you can also, on our right, you can see a flow or a flow chart of how the machine learning model could be operating on. We do study the problem. Then you train the ML algorithm depending on the data, evaluate the solution, analyze the errors. So you keep on iterating the process until you are sure that the accuracy percentage is reached. Then you can go ahead and launch. Now, under machine learning, we do have two main categories. That is supervised learning, which requires a human-labeled data set that provides the necessary supervision during the training of the algorithm. Then, unsupervised, the algorithm uh, can learn without any supervision, and it doesn't require any labeled data set. Supervised machine learning can also be broken down into types. That is regression and classification, where regression is mainly concerned about uh, continuous data type of numeric data in such a way that it's mostly dealing with numbers. Say, for instance, prices of fuel or prices of houses. Then for classification, it's more on the categorical discrete data. Such as identifying the features, differentiate between maybe a cat and a dog, a spam email or not. Then for unsupervised, it's also broken down into two main categories. One, we do have the clustering, which involves grouping together features that exhibit the same characteristics. An example which you can take is a recommendation engine uh, that recommends the different users who are using on Netflix. Also, the a Google search engine, which uses keywords to bring out the cluster web pages. Then the anomaly design for it is detects unusual currencies. Like for instance, if you're having outliers in the data, and the best example which you can give is mainly detecting a fraud on credit cards based on the money which is being spent. You can give an example, maybe the average range of the person being using the credit card, maybe it was in $200. Then from nowhere, you're noting a transaction of maybe $20,000. And then for under the supervised learning, we do also have linear regression, which describe the relationship between variables in a linear function. It works the same. It's similar to the mathematical linear function. It finds the relationship between the features. Features is what we are using to train, and a label. A label is what our target value is. It uses the basic equation, which is y prime equals to b. Y is what we are trying to predict. B is the bias, W is the weight, sometimes also referred to as the slope. Then X is what we use uh, to train our model. Then under the mathematical and statistical model, we do have, remember, model is just a representation of some of the phenomena. So we do have what we call the deterministic models, which are more concerned about the exact relationship of the data. So it doesn't have randomness in it, and is suitable when prediction error is negligible. So it takes that assumption that the error is negligible. Then for probabilistic, for it, it has that randomness of the error. So it uses two components, that is the deterministic and also the random error. Then we also have the gradient descent, which is a mathematical optimization technique used to find the local minimum of a function. It is an iterative algorithm that takes small steps towards the minimum in every iteration. So the gradient descent is usually used for minimizing the error where we are having a cost function. So when the learning rate is high, this means that the algorithm will take, sorry, it is low. When the learning rate is small, the algorithm will take in a lot of steps to reach the global minimum, and it will always find the accurate value. Whereas when it is large, the algorithm will be taking large steps and it is bound to fail. And so the probabilistic model, it has three main types. We do have the regression model, we do have the correlation models, and other models. But mainly, we shall just start based on the regression models, describing the relationship between a dependent variable and an explanatory variable. A dependent variable, it would be from our linear function. That would be the y, or what we are trying to predict. Then the explanatory variable would be our x, the data that we are trying to feed in or to trying to test. So it takes four main steps. One, we hypothesize the deterministic component. Then after that, we specify the probability distribution of the random error term. After that, we shall evaluate the model depending on on the fitted model. Then you use the model for prediction and estimation. This is where you are launching the model uh, after the above steps. We do also have what we call the least square, which helps us to find the baseline of it during when we're drawing our linear model. So take for instance from the data that we're having here, the baseline of is the difference between the actual and the predictable value. So the actual values are the one where we are having our linear model, where it is passing through. Then we are trying to the least squares the cost, which is from, take for instance, from this training set to our linear model. So that's the cost function for the least square method. Um, and then in this slide, we are talking about the key nearest neighbors. The key nearest neighbors. But before getting to that, we need to have a view of the parametric and non-parametric models, because the KNN is an example of the non-parametric models. So for parametric, this here, you know the exact model fit to the data, such as using the regression line. So you know the exact function that you're going to use. Whereas for non-parametric, the data determines the regression shape. It decides on how the function will look like. And KNN is an example of the non-parametric supervised learning classifier, which uses the proximity to make the classification or the prediction about the grouping of an individual of individual data points. So take for instance from our visuals that we are having here. So the algorithm will calculate the distance between the training data and the test point. So we are trying to calculate the algorithm from this blue circle to the test point, which is the star red, uh, uh, the red star, and also the distance of the green circle, then also this. Then after you find the k nearest neighbor, here the k nearest neighbors are three. So you're having 1, 2, 3. Then you classify based on the majority vote. And for the majority vote here, we shall end up saying that the red star, the training or the test point is green, since green has more points in the k-nearest neighbor compared to blue. Key considerations for the KNN. One, you should avoid using test data for hyper parameter tuning, because our goal is to perform well on our goal for the ML for the machine learning is to perform well on unseen data, not data that we are trying to use in the test or in the prediction data. Then use the Euclidean distance for similar dimensions, where we are having maybe we are having a depth, we are having length. There we shall be using Euclidean distance. Then where we are having age, weight, where um, the dimensions are dissimilar, we shall be using the Manhattan distance. Then we normalize the features with the different scales, but equal importance. Some of the key application, we have test mining, we do have agriculture, finance, and also in the Kaggle competitions. Some of the pros, one, it is easy to explain and it's simple to understand. Given the example that we did, it's easy to find the majority. Okay, neighbors, there's no assumptions on data distribution. It also works for regression and classification, so it works for both supervised learning, then suitable for multi-class or multiple data sets. And some of the disadvantages is inefficient to large data sets, as the dimensions will be much. And the prediction step is computationally expensive, since we shall need to compute the proximity of each data set, and then sensitive to skewed class distribution and also cannot handle missing values. So when we go to, so hold on just a moment. So the other thing that I'm touching about is decision tree, which is also an non-parametric supervised learning used, which is utilized for both classification and regression tasks. It's in a tree structure and consisting of the root nodes, branches, internal nodes, and the leaf nodes. For the root nodes, this is the starting node or the starting decision. Then internal nodes, it represents the features of the data sets. What are the attributes in the data sets? The branches, these represent the decisions, rules, which we are taking for every data set. Then the leaf node, this will represent the outcome. They are always at the end of the tree. So the decision tree algorithm, one, the first step is to find the best feature. What kind of feature is mostly being exhibited in the data set. Then you split the best feature. You split for the best feature. So you split the database depending on how on the majority of the features. Like usually it's always like a two-way. Then you partition classes. You divide them into classes based on the first and the second step. So heading to the next slide, where we are talking about the Gini impurity. This measures the probability of an incorrect classification if a random sample is classified based on the distribution of classes in the dataset. The Gini impurity, entropy, and pruning, they are widely used functions for the decision trees. So for ranges between zero, the range of the Gini impurity is between 0 to 0.5. Whereas as a value of 0 means there is pure classification. So it's only one class. An example, if 90% of the samples are class A and 10% are in class B, then adding impurity we shall be computing, then subtracting, which will give us a 0.18, as you can see from our working examples we are having here. Then when you talk about entropy, this quantifies the level of uncertainty or disorder in a data set. So when it's at maximum.
My slides.
Okay, that's fine. It's fine. You can go ahead now. Please, you can unmute and go ahead.
From my colleague. Okay, thank you very much, Mr. Sharif. So to continue, we shall continue with entropy. And entropy, like just as we have seen, Gini impurity, where Gini impurity measures the probability of an incorrect classification if a random sample is classified based on the distribution of classes in a data set. Entropy, however, quantifies the level of uncertainty or disorder in a data set. And for it is more of a logarithmic function. That's why if you see from here, removing this branch helps us to reduce the overfitting problem in these decision trees. So there are two types of pruning, that is pre-pruning and post-pruning. Whereby under pre-pruning, we halt the growth of the tree based on conditions like max depth and minimum samples. And then in post-pruning, we are removing branches from a fully grown tree to balance accuracy and complexity. So since we've covered most of these parts under artificial intelligence, so I won't go too much in detail, but that's pruning. So, and then, so we have the pros and cons of decision trees. Now, these decision trees, the pros, they are easy to interpret and visualize. This is because they depict human decision-making processes, and since they consist of nodes and branches, just as you can see here, we have nodes and branches. So these trees are very easy to interpret, and they are very easy to read and follow. For instance, here we have an example whereby we are determining whether someone will do something based on a given condition. That is, for example, here we're saying that someone will play tennis if the weather is either sunny or not. So we are saying that if it is sunny and that is meaning the humidity level is greater than 75%, then someone will not play. And if it is less, someone will play. Then we have a non-parametric, meaning that unlike other models such as linear regression, decision trees do not assume that the data flows in a specific distribution they don't have a normality. So this makes them very robust for real-world data sets. Remember, other models, we assume that if it is a straight line, it's a straight line. If it's a curve, it's a curve. But that's not the case in decision trees. And they handle nonlinear patterns. Just as I've said, we are not assuming that everything follows a specific pattern. So this makes them very powerful for datasets which don't have a straightforward linear correlation. For example, where the increasing price doesn't always reduce and they can still be handled well by decision trees. In a situation whereby we have values which can change, say you have a 1 and a 10, and then you have a 14, you have a 20, so that's not something very linear. And then the minimal pre-processing. Decision trees require little preparation for the data, and they work well with the raw data without needing complex transformations, scaling, or normalizing the features. And examples, we have the SVM and KNN decision trees, which can directly handle categorical variables like sunny, rainy, binary flags, etc. They are versatile. They support all types of data. That is binary, categorical, continuous. So binary data, this is either true or false, male or female. For example, if you're in, let's say, in a learning platform or environment, you have either completed or you have not completed. And then categorical, let's say you're either doing web, there is mobile applications, and either programming languages. So that's categorical data. And then continuous, that is we have things like age, temperature, salary. So in let's say in an e-learning platform, we have the engagement time. That's the continuous data. So these decision trees can handle all those types of data, and they can also handle regression tasks, not actually classification, and they can predict continuous values. And so next, we have the cons. They are sensitive to noise. If data is not very clear, it can grow. Remember, these are trees, so it may create very many other branches so as to try to fit it perfectly in your, to make a better description. And there is instability. They're highly sensitive to changes in input data. That is, a slight modification can alter this tree structure. And then they are biased with the imbalanced data sets. They tend to favor the majority class in an imbalanced data set because they prioritize splits with higher overall. For example, in a data set where 90% of records belong to class B, the tree might classify almost all data as class A because it achieves better accuracy, ignoring minority class B. So this has been seen commonly in those collaborative filtering models, whereby they come to a conclusion basing on, they give you a prediction. They say, like, since everyone has been doing this, it's good for you to do this. But sometimes which may not be the case if you're doing a recommendation model. So then there are greedy algorithms. They use greedy approach, meaning they will always try to go to the fastest minimal approach first, or they will do the conclusion basing go to, they always aim at getting to the point without considering its impact on the overall tree. So this can result in suboptimal trees. Next, we have ensemble learning, bugging, and random forest. So, and ensemble learning is a machine learning technique that combines multiple weak models to produce a stronger and more accurate predictive model. So here in our picture, we can see we have the data set, you have subset 1, subset 2, and subset K, and we have 3 models. So we're combining these models to come up with a prediction. So for example, so how it works, the individual models may not perform well on their own. So the model 1 may not perform well and so on. But when their predictions are combined through combine model 1 and model 2, and we can achieve a better accuracy and robustness. The idea is that different models may capture different aspects of the data and combine them, thus reducing errors. So an example, we have average predictions for regression problems. The final prediction is the average